Okay, so this is a run-through description of the data collection and aggregation mechanisms within the MDR, starting with an overview of the system and then looking in a bit more detail at the source material and the data collection processes, data aggregation, and then finally the file generation, which is the link to the next stage in the system. So, starting with an overview, essentially the data collection system in the MDR is a collection of databases. So for each individual source, there is a corresponding database, which is used to import the data from that source. So the sources are trial registries, data repositories, bibliographic systems like PubMed, etc. And for each source, there is a corresponding database. The data goes into there. It's then transformed by ETL, extract, transform, load processes that bring essentially the data together. So they aggregate it into a central database, but at the same time, they link it so the data objects are linked to the studies that generated them. And where necessary, deduplication takes place because studies and objects can be referenced in different source systems. For example, a trial can often be registered in more than one trial registry. So overlapping data, duplicated data, that has to be resolved into the core database here, which then acts as the single source of truth in the system. Once it's in the core, the data is available then to generate the JSON files, which are used to communicate with the OneData services and the Elasticsearch services provided by INFN, and those are in turn used to power the web portal. So in a bit more detail, the individual source-specific databases here actually consist of two groups of tables. One are called the session data tables, the other accumulated data. The session data tables receive the data from each individual import. So they're torn down and rebuilt for each import. And the process starts by identifying what data is required, and that may be the whole of the source, but normally try to make it the data in the source that has been recently revised since the last import or has been added. So we download that usually to a local copy first and then import it into the session data tables. There, the session data is compared with the data that's already been imported, and where it's been revised or it's new, it's added to that accumulated data, or the accumulated data is changed to correspond. At the same time, the data is recoded and restructured to match a single consistent scheme, the ECRIN schema that we developed, so that all the data from all the sources is in the same format. Obviously, it starts in very different formats. Once that's done, the data can be aggregated together within the central MDR database. And it's done initially by splitting it into the data that relates to studies, that relates to the data objects, and that relates to the links between them. That makes it easier to do the deduplication and aggregation processes. Once that's done, the data is then re-aggregated back into a single core schema within the database, and then it's available for file generation. Okay, so to illustrate the details of the system, we've selected this OmniHeart trial, partly because it has several linked data objects, and so it's a good example to illustrate the different aspects of the MDR system. So the OmniHeart trial has a clinicaltrials.gov entry. That's the web page. That data we obtain directly from clinicaltrials.gov as an XML file. And that happens to be the file for that study. clinicaltrials.gov is very good. It makes all of its data available as XML, and it's relatively easy to download the whole of clinicaltrials.gov or just the recently revised material and to feed that into the system. So the OmniHeart trial also has a collection of journal articles associated with it. One of them is here. This is the PubMed abstract. And again, we need that information to feed it into the system to obtain the details about the journal paper, put it in the MDR. Again, PubMed makes their information available as XML files. We don't try and duplicate PubMed. It has over 30 million records. So we do try and identify the journal records, abstract records that are referenced by the studies in the system, or which themselves reference trial registry IDs, which is some of the entries in PubMed do. So we download the abstract details and the trial registry details from the various sites as XML. But this trial is also listed by the National Heart, Lung and Blood Institute, part of the NIH, on their BioLink site. Now, BioLink is very useful from the MDR's point of view because it contains information about other data objects linked to a study. So it's a useful source of data. But of course, we are duplicating data now available elsewhere. And we also have to get this data not as XML, because BioLink does not make the data available as XML. Instead, we have to scrape it off of the website. So we go to the underlying HTML code on the page and basically take out the relevant data points from that. Because BioLink and similar sites, the web pages are constructed from a database in a consistent fashion. It's relatively straightforward to scrape that data off, although of course each site requires a different scraping process. So we get the data down in these various formats and then feed them into the system using a suite of programs. The code for the processes is all available on the ECRIN's GitHub site. There's a list of the various small programs that are used. At the moment, they're separate. The plan is to consolidate these into a single system. Each individual project shows the files that are involved in it. Most of them are available, and all of them will be available as open source. They are under an MIT software license, and most of the all contain a README file which gives a brief description of what the project's about and its provenance. And of course, you can drill down on the GitHub site into the code. This happens to be the code that scrapes data from BioLink, or part of it, and it's just going through the HTML and identifying the nodes of interest and then pulling out the various values of those nodes and their attributes and then transforming them into the ECRIN system, ECRIN schema for storage. The GitHub site also contains the database scripts that are used to aggregate and deduplicate data. So this is mostly done in SQL within the database, this process. And again, you can drill down into the SQL statements that do that. It's a whole collection of SQL scripts that are run to do that aggregation and deduplication process. Another useful resource to understand the system is the project's wiki. We run a wiki. It's not always up to date with the most recent developments in the system, but we try and catch up when we can. But that has a whole range of information about the system, how it works, including a definition of the ECRIN metadata schema. And this is the system, the schema that we translate all the source data into to make it consistent across the different sources. And so there's a list of data points for studies and for data objects. And this page describes all those in detail. The wiki also provides details about the database, for example, and the control terminology used within the system. For example, the attributes, some of the attribute types that we apply to studies, for example. But there's a whole, as I say, a whole range of information there. Once the information has been imported and processed, it ends up in the core database. We use Postgres, because it's open source and it's free. So we use Postgres to store the data. This is the core schema within the MDR database, and it has, as you can see, tables describing the data objects, but also the data object attributes, and a table describing the studies and some of their attributes. The next stage is to generate the files. There is, again, the wiki has a description of the JSON schema that's used. This is for studies. So the JSON schema is essentially the JSON version of the metadata schema I showed just a few moments ago. And in the case of the OmniHeart trial, the study JSON that's produced, the file that's produced to represent the study is here. The ID here is an MDR ID, it has no relationship to any NCT or numbers or anything like that. And this has all the study attributes that are available for potential display in the MDR, the topics which are used for searching, different titles, and also a list there of related objects, of which one is 10451167, which happens to be this one. This is a JSON file for that object, and this happens to be that paper that we looked at the beginning, and it has all the attributes of that paper, its authors, and again its topics, dates, etc., identifiers. On it goes. At the bottom is a list of the related studies, and 1008-680 is OmniHeart study. So the study file is referring to the objects, and the object file is referring back to the studies. So those two files are amongst about a dozen that would be exported for this particular study, and amongst several 100,000 that are exported for the whole MDR. At the moment, we export about 850,000 files. We're soon going to try and increase that to well over 1 million as we bring in more trial registries into the system. Okay, thank you very much.
So, to see how our use cases have been implemented and integrated into the overall system, first of all, I have to log in to the OneData platform. And to do that, I will use sign in as XDC member method. After that, I was redirected to the spaces page, where all the spaces which were created within a single one provider are represented. And here in general, we are interested in two different spaces. First space name is ECRIN V.1, and this space contains the studies and data objects, JSON files with the metadata related to COVID-19 clinical trials and which are used for our COVID-related metadata repository portal. And the second space name is ECRIN Demo7, and it contains studies and data objects, JSON files with the metadata, and which are used for our main let's say metadata repository portal version. So for now, let's take a detailed look at the ECRIN Demo7 space. To do that, I will click on Browse Files link. As you can see, I was redirected to the root directory, where you can see studies and data objects folders with the relevant JSON files inside. All these files were integrated into the system using OneData FS library, which is based on Python FS library and were adapted to work with OneData environment. All our JSON files stored in several directories with 10,000 of JSON files per each. To see that, I will click on Studies directory, and yeah, as you can see, all the files were successfully split between the directories. So let's take a look at random file, and let's select random study for that. And by clicking on information button, I will see all the necessary information of the file, like file name, file path, file ID, and space ID. And if I want to see the metadata which are attached to this file, I have to click on tag button. Because of our metadata are stored in JSON format, I have to click on JSON tab here. And yeah, as you can see, all the metadata related to selected file or selected clinical trials are successfully stored and attached. And this metadata structure is based on our own metadata schema for the studies, JSON objects. And the same thing is for data objects. So if I will open the random directory with the data objects and select the random data object file, I will see the information about the file and for sure the attached metadata in JSON format, which is also based on our JSON schema for data objects in JSON format, for sure. So now when we confirmed successfully that all the files were successfully imported and integrated, let's take a look at the discovery of these files. So I'll go back, and if I will click on Discovery tab here, I will see the list of the harvesters. And by the harvester, we mean the cumulative component with the web portal user interface and other necessary components and plugins like Elasticsearch. So, for example, if I will click on the metadata repository tab, I will be automatically redirected to the web portal search page. But let's go through other settings. So, for example, if I will click on the Spaces tab, I will see the list of the spaces which are connected to the harvester. In our case, is ECRIN demo 7 space, which is correct. By clicking on Indices tab, I will see the list of indices which can be used by the graphical user interface, by Elasticsearch, and by the harvester for sure. Here I will see the list of the members which have access to the harvester, and the most important tab is the Configuration tab, with the general information about the harvester like name, attached plugin, endpoint. The tab, is it publicly available or not, and if yes, there is a link, there is a URI to the web portal. And after that, if I will click on GUI plugin tab, I will see the GUI plugin settings. So for example, you can see that for now we use the latest version of the web portal plugin. It's 0.7, and this plugin can be easily uploaded by clicking on the Browse tab and selecting the necessary archive with the plugin source code. And then I have to click just upload button and it will be uploaded, but I will not do that because it is already done. In indices section, you will see the indices which are used by the GUI plugin and by the harvester, and in injected configuration section you will see the default configuration for the web portal. So let's go back to the web portal. Yeah, it works. And the last point is that let's check, is it really publicly available or not? Let's copy this URI and paste it to the new tab. So yeah, as you can see, the web portal is publicly available and can be used by the external users. Thank you.
Now I will demonstrate the functionality of the portal. Open the browser, enter the link, and then you will see the entry screen. You can search for studies by select mode specific study. You can select the type of ID trial registry here. You can enter a specific trial registry here from clinicaltrials.gov. You then click on Find, and you will immediately see the study found with the data objects linked to this study. And if you click on one of these data objects, you see here the registry entry in clinicaltrials.gov. Now you clear and do another search, also specific study. Now you look at study characteristics, and study title contains breast cancer. Again, click Find, and you find 1,000 trials containing breast cancer in the title. But there are more of them. And you click again on Find, and then you get 2,000 trials. You can look at the individual trials, at the documents available. You can click on Documents, again, registry entry in clinicaltrials.gov. Now you clear the search pattern again, and you add BRCA as study topic with an and if you click, you get 36 studies altogether. You can scroll them down. You can click on it. And now you can filter the studies. First of all, you select all the types, and you click interventional. And if you apply, you have 28 studies. But you can add more filters. You can add randomized. You click, and you have 15 studies, and you can enter phase 3. You get 6 studies. Again, you can click at the studies and at the various data objects linked to a study. So if you click on the data objects, you see the underlying data objects. So now we do a search again by looking for a specific study with a trial registry ID that we know. We type in the registry ID with a find, and we get the so-called OmniHeart trial. You can also type in OmniHeart under study title contains, and if you click Find, you get 2 studies, and the first is again the OmniHeart trial. Here you see many data objects belonging to the OmniHeart trial, and if you click on one of them, you get the study protocol. You can scroll the protocol. You can also click on a manual. You get the manual for the OmniHeart trial. Or you can click on a journal article belonging to this study, and you get from PubMed a publication about this study. If lucky, you also get the full paper